Hi there, welcome to my videos on elementary differential equation. This is video 6 for chapter 8 and the topic is Fourier series. In the previous video we went through a method for more efficient performance of integration by parts, and we call that the tabular method, and that would be very useful when we want to compute the Fourier coefficients. Okay, so let's take an example here. So here we want to find the Fourier series of the function Rt, which is defined as follows. So it's a periodic function with period 2 pi, and then we define the function on the interval from negative pi to pi, and then it can be repeated periodically. So on the interval from negative pi to 0, it's a linear function, is t plus pi over 2, and then on the interval from 0 to pi is negative t plus pi over 2. So the difference here is this the linear function t. So on the left side of the y-axis, this is a line with the slope 1 that goes positively upward, and then after that it bends and goes with the slope negative 1. We can quickly sketch this. Probably wouldn't take much of an effort. So let's say this is t, and that's my function. So it's a t, and this is function r. Okay, and this is negative pi, and then this is pi. And then we see when t is 0, I have pi over 2. So this is pi over 2, and this is negative pi over 2. Okay, so when t is less than 0, it goes up with the slope 1. So it starts from here and it comes up, and then on the interval from 0 to pi it has a negative slope of 1, so it will come all the way down here. Okay, and then it's periodic with period 2 pi, then you can extend it. So negative pi, negative 2 pi, negative 3 pi. Then over here from negative 3 pi to negative pi, it just repeats what we have here. So I will have a positive value here and come down. So you come up and come down. Okay, then the whole thing is just this going up with slope 1, going down with slope negative 1 periodically. You can extend it also on this side and furthermore to the left. Okay, now let's seek Fourier series for this function r, and let's write out. This is the Fourier series with a constant term and then cosines and the sine functions. So we have already done a couple examples for Fourier series, and we have the observation that is if the function is an even function, which is this function here, we can see from the graph we have drawn just a while ago, and if this is an even function, and then the even function times sine function which is odd, and the product will be an odd function, and then all the Fourier coefficients here will be 0. So we can conclude immediately all the bn's will be 0 for all n. And furthermore, we know that r times cosine, they are both even. Then the product is an even function. So it's symmetric about the y-axis. If you integrate a period symmetric around it, we only need to integrate half of the period, let's say from 0 to pi, and then multiply the result by 2. This simplifies quite a bit the computation. Okay, now let's compute. So it's wise to compute the A0 separately, even though the formula is the same, but then the details are always different. Okay, so A0 is 1 over pi, the integral times Rx. And since we know that's an even function, we only need to integrate from 0 to pi and multiply the whole thing by 2, and we put the function here. And this integral is 0. you can work it out, or you can recall the graph. Remember, let's quickly draw the graph here. So on the interval from 0 to pi, the graph is pi over 2, and then down here is negative pi over 2, and it's a straight line. Okay, if you want to integrate this, then you look at this area and this area that's above the x-axis, that's below, and it's symmetric, so this is negative and cancels the positive, so it's 0. Okay, and then for n bigger than 1, we have to work out the integration. So this is the formula for compute an, and then put in our observation. We just need to integrate from 0 to pi and multiply by 2 of the function r here times cosine. So we see that we are facing an integral of a polynomial of degree 1 times a cosine. So recall the tabular method we introduced in the last video, and let's try to use it to perform this integration. Okay, so here we set up the tabular and column A and column B and the product column. So column A, we put the polynomial function in the column A, and then we differentiate it in t. Differentiated once, we get -1, and differentiate this one more time, we get 0. Then we know we can stop. And then for the column B cosine function, we find the integral, the antiderivative. So for cosine, we get sine, and don't forget the constant term here. And then integrate this one more time, we get back cosine, but then we pick up a negative sign, and we have another 1 over n multiplied on it. Okay, then we can stop because this is already 0. Now let's write out the diagonal term. So the first one will be this one times that, and it directly goes in here. Nothing needs to be done. And then for here, we'll have this term times this term goes here, and we need to remember to add a negative sign in front because the signs are alternating, positive, negative, if there shall be more terms down here. Okay, and then that's it. Okay, now we can write out the integration. So the integral would be collecting these two terms, which we write over here, and then there is also the coefficient 2 over pi, and this is evaluated for t equal to 0 to pi. Now for the first term, we will have sine 0, which is 0, and then we'll have sine and pi, which is also 0. So this term is 0, it doesn't contribute anything. And then we have this term, so when t is pi, we get cosine n pi, and with this constant, -1 over n squared, minus when t is 0, and this cosine 0 is 1, so minus, we get positive 1 over n. Okay, so we can take out the common factor 1 over n squared. We get 2 over pi n squared. And then this is just 1. And then we have cosine n pi. So remember in the previous video we calculated cosine n pi, which is -1 to the power n, because it takes value between 1 and -1 and alternate between them as n increases. Okay, we can further write out. It's worthwhile to write this out because we observe that when n is an even number, -1 to the even power becomes 1, then this is 0. So we have actually half of all these coefficients are 0. Okay, and it's only non-zero when n is odd. When n is odd, this becomes -1, and then it becomes 1 minus -1, that's 2, so we get 4 over n squared pi for n odd. Okay, now we are ready to write out the Fourier series for the RT. So we see that there are no sine terms, there are only cosine terms. And then in this summation, we actually have lots of zeros, so we only need to sum over n, which is odd. And then when n is odd, an is 4 over n squared pi cosine nt. We can write out the first few terms just to get an idea to see what they are. So that becomes 4 over pi, which is common, and let's put 1 over n squared in with a cosine together. So when n is 1, I just get cosine t. And then when n is 3, I have 1 over 9 cosine 3t. Then when n is 5, I have 1 over 25 cosine 5t. And then for n is 7, I get 1 over 49 cosine 7t, and so on and so forth. Okay, so it is always interesting to observe the behavior of the partial sums and to see how well it approximates the original function as you pick more terms. So let's write out maybe the first 4 partial sums. So y1 is just taking one term, that's cosine, and y2 will be taking 2 terms, these two, and they're here. And then y3 is taking 3 terms, as we see here. And then y4 will be taking 4 terms, which we write out here. Okay? Or you can easily add more terms and observe more terms of partial sums. So next we are going to plot these partial sums against the function rt and see how it behaves. Okay, so the first plot is the partial sum for y1, which is the top graph, and the original function r is in blue, which is just the triangle, called triangle wave. It just goes up and down with slope 1 and -1. And the orange color is the Fourier series partial sum y1. Okay, and then we're interested in the arrow, so let's plot the arrow. Here is just the r minus y1 at every point, and it's a graph like that. So the range for the y1 is from -2 to 2 in the plot, and for the arrow is from -0.3 to 0.3. Okay, and this will be fixed for all the plots, so you can see how the arrow decreases. Okay, and one observation one can make is that we see that the arrow has some peaks. So it's periodic and has peaks. So where are these peaks? Where do they occur? Well, if you trace it back to the original function plot, and you see that the peak of the arrow occurs at the point where the function r has a kink, means where the derivative of this function r is discontinuous. At this point, and then again at this point, and at this point. And in between, we see the arrow is smaller. Okay? Okay, so here is a same plot, but for y2. And as you see that, we see it's already pretty close. The orange curve is pretty close to the blue one, which is the r function. And then we plotted the arrow in the same y-axis scale, and then you see that it's much smaller than the previous one, and the peak occurs at the same location. Still here, they have a peak. Okay, so here is the next plot of the partial sum y3 against the original function and the arrow. So let's make the similar observation. We see that taking 3 terms, the function, the Fourier series, the partial sum is in the part where r is a straight line. It's really close. It's already hard for the eyes to see the difference. At the point where r has kinks, and you see the arrow. Okay, it's confirmed by the plot of the arrow, and it's very small here, but then there are some peaks, and the peaks are at those points. Okay, so one more plot for y4. It looks like it's even better. the approximation of y4 to function r. And if we look at the arrow, it's even smaller here, and also the peaks are smaller. So everything looks good. Okay, so here is a plot of plotting everything together. It's a bit difficult to see from this plot if I didn't go through the previous ones. But if we go through the previous ones, then you can see that this is the y1, and then y2, y3, y4. It gets closer to the function r, and also the arrow for y1 is quite large. But then as you add more terms, for y2 the peak occurs here, and then for y3 is here, and for y4 is here. It gets smaller and smaller. Okay, let's make some observations, and it's always important to observe patterns. And first we see that in general the arrow decreases as we take more terms in the partial sum. And second, for a fixed partial sum for any of the function y1, y2, y3, or y4, we see that the arrow is larger at the point where the function r has a jump or a kink. Okay, so in this one we would go back to the function that is discontinuous, and that's the observation we made over there. And for the previous example we just had, we have kink. Okay. And then the arrow is smaller in the region where r is smooth or straight line. So for this example, we see that after taking 3 terms, the partial sum is already a very good approximation to RT, especially in the region where r is smooth. So now that's just conjecture. So from this observation, we say it seems like we haven't proved it yet. Okay, it seems like that the partial sum y and t seems to be convergent to RT at every point t as we take more and more terms, that is, as n goes to infinity. Okay, so a theoretical discussion on the convergence of Fourier series will come later. Okay, so before I end the video, let's take one more example. I call it a dummy one, but it might be useful. Okay, so we are given a function f of x, periodic with period 2 pi, which is given like that. And I ask you to find the Fourier coefficients. So the function is 2 plus 4 sine x, negative 0.5 cosine 4x, negative 99 sine 100x. So the special feature of this function here is that the function itself is already given in terms of sine and cosine function. These are the functions that would occur in the Fourier series. And when that happens, there is actually no need to carry out computations of the Fourier coefficient, because we already know the constants in front of the sine cosine function are the Fourier coefficients. We only need to identify which coefficient it is, the index. Okay, so let's look at the a's. The a's are the constant terms and the cosine terms. So we see that we have a constant term, 2, so a0 will be 2 times that, which is 4. And then we have a cosine function, which is here cosine 4x, and that will give us the coefficient a4, which is negative 0.5. And we don't have any other cosine functions, and then we can say that all the other coefficients a(n)s are 0 for all n does not equal to 0 or 4. Finally, we can look at the coefficients for the sines. We have 2 sine functions. One is sine x and the other is sine 100x. So what's in front of sine x will be the coefficient b1, because it's sine 1 times x. So b1 is 4. And then for this coefficient here, it will be the b100. So b100 is negative 99. And then we can conclude all the other bn's are 0. All the other bn for n different from 1 and 100. Okay, so that is all for this video, and I hope it's useful, and I hope you enjoyed it, and I'll see you next time.